Before there were planets around the Sun, there were rings. Much like the way material orbiting Saturn is flattened by centrifugal forces into a tight, neat disk, the same happened with the Sun in the earliest days of the solar system, and the way those rings were composed explains how Earth grew from those rings into a manageable size and not into a so-called super-Earth. Super-Earths are rocky terrestrial worlds around other stars that are substantially larger than our own Earth, the largest rocky planet in our solar system, and which make up about 30% of the rocky exoplanets we've discovered so far. We avoided that fate, it turns out, thanks to pressure bumps in those early solar rings, according to a new study published in the journal Nature Astronomy. An international team of researchers from Rice University, University of Bordeaux, Southwest Research Institute in Boulder, Colorado, and the Max Planck Institute for Astronomy in Heidelberg, Germany, ran hundreds of supercomputer simulations to recreate the formation of the solar system. What they found was that 3 bands of high pressure in the early solar accretion disk can account for everything from the composition of the asteroid belt between Mars and Jupiter and the formation of the Kuiper belt beyond Neptune, but also the nearly circular orbits of the 4 inner planets, their composition, and their various sizes. Our model shows pressure bumps can concentrate dust, and moving pressure bumps can act as planetesimal factories, Rice University astrophysicist Andrei Isidorou, who led the study, said in a statement. We simulate planet formation starting with grains of dust and covering many different stages, from small millimeter-sized grains to planetesimals and then planets. We propose that pressure bumps produced disconnected reservoirs of disk material in the inner and outer solar system and regulated how much material was available to grow planets in the inner solar system. Had the disk been uniform, or smooth, in its composition, then the solar system would have a much different makeup than we see today. In a smooth disk, all solid particles, dust grains or boulders, should be drawn inward very quickly and lost in the star, Andrea Isea, an associate professor of physics and astronomy at Rice and co-author of the study, said. One needs something to stop them in order to give them time to grow into planets. At these pressure bumps, gas is denser and gas particles move faster, which in turn helps slow down the drift of heavier solid material like dust and rock, allowing it to start to accumulate into planets. The key, the researchers believe, is the quick formation of the second, middle ring in the solar disk. When they ran simulations with a late-forming second ring of material, this allowed much more solid material through into the inner solar system. This led to the formation of super-Earths, but a fast-forming second ring led to a solar system much like our own. By the time the pressure bump formed in those cases, a lot of mass had already invaded the inner system and was available to make super-Earths, Isidorou said. So the time when this middle pressure bump formed might be a key aspect of the solar system. Super-Earths aren't necessarily like Earth, just bigger, since the math and physics of the universe tends toward larger rocky bodies having substantially greater gravity as their radii grow larger. If the Earth were 10 times larger, assuming the same density as our own Earth, which it would be if its composition was proportionally the same as it is now, Earth's gravity would also be 10 times greater. So, if you weighed 100 kilograms on Earth, you would weigh 1,000 kilograms on the super-Earth, and our muscles and skeletons would need to be much, much stronger to support that additional weight. It would be like squeezing all of the mass of a fully grown bull into the human frame. It would radically change the way life on Earth developed, if it were able to develop at all. The increase in gravity also has important implications for whether a protective magnetic field could develop. Without one, UV radiation would have killed most life on the planet and the solar winds would have stripped away a lot of our atmosphere, which is what we suspect happened to Mars. Knowing the conditions that will allow life to form as we know it, then, will help us narrow down which exoplanets are more likely to have life on them. And given the limited amount of resources we have for the search, the more we can shorten the list of candidate planets, the better our odds of success. That's it for now. As usual, fellows and ladies, thank you all for coming in and watching. See you in another video.